In this playlist, I'm showing you how to build a CPU. If you haven't watched the previous video, check out the link to the playlist. In this video, we will introduce what a transistor is and show how to use transistors to create a NAND gate.
I can't wait.
We note that transistors are electrical components, whereas NAND gates are Boolean logical constructs. So, an important aspect of this video is how we move to a higher level of abstraction, or in other words, from transistors to Boolean logic. There are two big ideas that make electronic computation possible. The first of these big ideas is that all computation boils down to simple functions, or in other words, mechanisms that have inputs and outputs. In fact, for digital computation, these functions may be limited to Boolean and binary functions. The second of these ideas we call abstraction. Abstraction is where we hide the complexities of a system so that the system appears to be as simple as its interface. Or in other words, its inputs and outputs. Abstraction allows us to manage complexity, to be able to understand and navigate complex systems. We can dive into the nitty-gritty details of some subsystem, but then use abstraction to become unconcerned by those details as we move to a higher level. Then, at the next higher level, we can consider another set of details, and so forth. We will use both of these ideas throughout the videos in this playlist. In the previous video, we built the circuitry of the simplest of all Boolean functions, the identity function. In this video, we will build on the idea of the identity function and create the basic building block of computation. In later videos, we will apply abstraction to this basic building block to build fundamental Boolean operations. Then, we will apply abstraction again to build higher-level digital functions. Finally, we will apply abstraction to these higher-level digital functions to create an arithmetic logic unit, or an ALU, and processor like the ones described in the first video in the playlist. Let's start by considering the circuitry we built in the previous video that created the Boolean identity function. Recall that the Boolean identity function just outputs its input. We built this function using a circuit that had several components connected in series. For this next project, let's look at a circuit that has a parallel path. We can create this circuit by modifying the circuit we built in the previous video. First, let's imagine what would happen if we took the previous circuit and removed the switch. To remove the switch, we connect the positive lead from the power source directly to the resistor where the switch used to be. Here's the schematic for this circuit. What would we expect this circuit to do? We have essentially replaced the switch with a wire, so it's as if the switch were always closed. Previously, when we closed the switch, the LED illuminated, so we would expect the LED in this circuit to remain constantly illuminated. Let's try this out and see what happens. It was pretty easy to figure out how that circuit would behave, but let's take a look at one that is a little more complicated.
Is my punishment still coming, or is it just the horrible staring because the anticipation is killing me?
What if we take the circuit we just made and we add a switch in parallel with the LED? How do we expect this circuit to behave? You may want to pause the video here and see if you can predict how the circuit will behave. If we think about the circuit, we can see that when the switch is open, the circuit will behave exactly like the first circuit we made in this video, the one with no switch. When the switch is open, the two circuits are the same, and the LED is illuminated. However, the question to answer is, what happens when we close the switch? If we build the circuit and test it, we see that when we push the button and close the switch, the LED turns off. Why does this happen? Well, when we close the switch, we give the electricity another path that it can take. We need to ask ourselves, which path is easiest for the electricity to follow? Or, in other words, which path has less resistance? It turns out that the switch, when closed, has no resistance, or at least no more resistance than a wire, which is very small. However, the LED does have some resistance, not much, but more than the switch. Therefore, The electricity travels through the switch and avoids the LED, which causes the LED to turn off. Now let's think about what Boolean function this new circuit represents. When we push the button, or said another way, when we input true, the circuit responds by turning off the LED, or outputting false. On the other hand, if we release the button, or input a false, the LED illuminates, which indicates true. If we write this out as a truth table, the table looks like this. What Boolean function is this? This is known as the Boolean NOT function. The Boolean NOT function merely inverts its input. Up to this point, we have seen two circuits that simulate Boolean functions, the identity function and the NOT function. Both of these circuits, or functions, have only one input. What if we wanted to simulate a function with two inputs? What would a circuit like that look like? Well, if the button represents a Boolean input, we can see that a circuit with two inputs would require two buttons. There are lots of different functions we could model with two Boolean inputs by placing the switches in various configurations.
What configuration?
But we can easily create one simple and very useful function by modifying the previous circuit. Let's add a second switch in series with the first switch. Check out this circuit. If we think about this circuit and compare it to the previous circuit, it becomes clear how this function behaves. With both switches open, the LED is on. If we close only the top switch, the LED remains on. Also, if we close only the bottom switch, the LED remains on. However, if we close both switches at the same time, the LED goes off. So, what does the truth table for the functionality of this circuit look like? As we can see, for this truth table, we need two input columns corresponding to the two switches, and a single output column corresponding to the LED. This function is a bit more obscure than the identity function or the NOT function. This function is actually a composite function. It might be easier to recognize if we were to invert the output. When we invert the output, we see that the only time the function outputs true is when both inputs are true. We can recognize this as the Boolean AND function. But since we inverted the outputs, it's not exactly the AND function. Instead, it's the NOT of the AND, which is known as NAND. It turns out that the Boolean NAND function is significant for two reasons. First, it is extremely easy to build. And second, here's the big one, all other computational functions can be built up from various combinations and configurations of NAND. What does this mean? It means that if you tore apart all the logic in your computer, if you decompose the logic into its atomic parts, you would find a bunch of copies of this circuit. Computation all boils down to NAND. But in order to use these NAND circuits, we need to build them in such a way that we can have the output of one NAND circuit be the input for other NAND circuits. To do this, we need to introduce another electronic component.
Please introduce one of them to me.
This new component is called a transistor. The first transistor was invented at Bell Labs in 1947.
Hey, Scott!
A transistor can be used for various purposes, but in digital electronics and computation, we use transistors as switches that we can control electronically. So, using transistors, we can connect the output from one NAND circuit to the input to a different NAND circuit. We'll investigate how to do this to form the basic Boolean functions in future videos. But for the remainder of this video, let's look at how a transistor works and how we would plug it into our NAND circuit. Unlike the electrical components we have seen so far that only have two leads, a transistor has three leads. These leads are called the collector, the base, and the emitter. Let's look at a drawing of a transistor. This drawing shows a transistor from the bottom view and from the side view, as well as the schematic symbol. The bottom perspective shows that the transistor has three leads, numbered 1, 2, and 3. We see from this bottom view that the transistor has a flat side to help us orient which lead is which. The leads are mapped as follows. 1 is the collector, 2 is the base, and 3 is the emitter. The side view isn't very helpful, but indicates how the leads look from the side. The schematic symbol has the leads labeled to indicate how the leads in the schematic map to the leads on the physical device.
Oh, I get it.
The way the device works is that lead 1, the collector, acts like the positive side of the switch. Lead 3, the emitter, acts like the negative side of the switch. Of course, switches don't have polarity, but transistors do. So when we say the positive side of the switch, we mean the side of the transistor that attaches to the positive side of the power supply. Lead 2, the base, is the input that controls the switch. To close the switch, we apply current at the base. One more point about using the transistors. Often, it is important to put a resistor on the base to protect the transistor, much like we did with the diode. Here's the NAND circuit, with transistors replacing the switches. In this circuit, the 3 resistors can be about 1 kilo ohms each. We see that we still have 2 switches, but this time the switches perform a different logical function. Previously, the switches were part of the NAND functionality. In this circuit, the switches simulate circuits feeding inputs to the NAND functionality. This is a subtle distinction, but an interesting one. So, where we see the switches in this circuit, we can imagine that they represent some other more complex circuits, each with a single output. As we mentioned, this circuit forms the foundation for all digital computation. In order to encapsulate this NAND functionality so that we can reuse it as a building block, we create a new schematic symbol to represent the relevant parts of this circuit. The symbol for NAND looks like this. We notice that this symbol has 2 leads on the left and 1 lead on the right. The 2 leads on the left are the 2 inputs, which are essentially the same thing as the 2 switches in the previous circuit. The lead on the right is the output, which connects to the anode side of the LED. The schematic doesn't show the power source connections. That is, the positive and negative power source connections at the top and bottom of the transistors. As our schematics get more complex, we don't show the power connections because they tend to clutter up the schematic. Without the power connections, the logic of the circuit becomes clearer.
It's all so clear now.
Congratulations! If you have followed the explanation in these videos up to this point, you understand the foundational basis for all electronic computation. In the next video, we will investigate how to connect NAND circuits together to create more useful Boolean functions. Subscribe and click the notification bell so you can be notified of future videos.